Hello, how are you?
I'm so hot. Yeah, I'm good.
Yeah,
Good week.
You excited for today's paper room?
I am. Yes. This is touching natty stuff. It's always natty stuff. I need to diversify my vocabulary.
What's a good synonym for natty?
There is none.
No?
Cool. That's such a bore.
In German, Josie would say mega, like mega, like mega.
Alright. Let's see if I remember that partway through the chat.
So how has your day been so far?
Yeah, it's been alright. We've been putting our what am I thinking? Our future seer? Like our seer hats on. We've been looking into the future, casting our gaze years down the line. Which is entertaining. It's
Stuff.
It's entertaining.
Mate, I am officially broken up for summer holidays, so
oh yeah,
I don't have to teach for 6 weeks, which on the one hand is great. It's nice to have a little break, but on the other hand, I do miss it when it's such a long time. You know,
I bet.
I really do.
I think I would.
I do miss it.
I can't imagine not doing the thing that I do.
I know.
It's nice to have time off. But...
yeah, don't get me wrong, it is nice. We will hopefully make the most of it. So we've got some of Josie's family's coming over. Some of her friends are coming over because they're going like wedding dress shopping, which will be exciting. We're going to Wales to see my buddy Dan, which will be lovely.
Nice.
Me, my mum, and my sister have all committed to hanging out at least once a week. So we'll see if we manage that for the whole 6 weeks. But I'm optimistic, and it'll be really fun. And I really need the help in the garden from my mum. She's an absolute gardening whiz, and I can't stand gardening. I really hate it, so I really need her help.
Yep.
Don't die.
No, I'll try not to. Nice. Yeah, that sounds good. What are you going to do in your garden? This is such a tangent. What are you going to do in your garden?
Just tidy, basically. We need to de-weed the front garden. I don't know. I don't really like my garden. I don't like it.
It's functional.
It's a little green space, but ultimately it's a bit of a mess. But yeah, there you go. That is what it is.
I'm pretty happy with our garden. Our garden's good now.
Your garden's lovely.
It was a state, and now it's functional. Yeah, it's above functional. It's good.
Yeah, it's a lovely garden. It does exactly what it needs to do, and you've got space to put the pizza oven when you need it.
Yes. Oh, yeah. That was dinner the other day.
Pardon? Did you have it the other day?
Oh, yeah.
I'm very jealous. Very, very jealous. So, what are we talking about today, Jamie McMillan? Oh, wait, we should probably do like a little hello and welcome to the podcast segment, because we haven't done that yet. So, hello. Welcome to Osmosiscast. Yep. This is season 2, episode 4? We're on 4, aren't we? Yeah, it is 4. I don't know why I thought it was 5 for half a second there. So this is season 2, episode 4. And my name is Callum Morris. His name is Jamie McMillan. Jamie, what are we talking about today?
Today is superconductors. So more like cutting edge science fields, but even more cutting edge than just superconductors, room temperature superconductors, which I don't know if you know anything about superconductors, that's even more crazy than conducting superly. Yeah. So
the brief for this episode came from my cousin, who I'll shout out again, who wanted us to talk about hoverboards. We couldn't find any good, meaningful papers about hoverboards, so we went for the next best thing, which was hover trains, which led us obviously to superconductors. And so the paper we're looking at today is actually quite a famous paper. This is the LK-99 paper, the first one that was put onto the archive. My understanding of LK-99 is that it's since been very much sort of debunked. I don't think it is a thing. But, I mean, our podcast didn't exist when this paper came out. So the fact that we're talking about it now, that's just an affectation. And I think that there is there's still plenty for us to sort of get our teeth into today. So,
Oh yes.
let's start with the paper. We will skim through it because, like you say, it's kind of a bit of a spoiler, but everyone who's anyone, or rather everyone that is a little bit of a nerd, will probably know that this is not a thing. But we'll touch on it anyway. Yeah, well,
Yes.
I mean, I think it's fair. It was in the news, like the mainstream news, wasn't it? So,
oh yes,
we're just very late to the party. So, talk to me.
All right, paper we got today. This is titled "The First Room Temperature Ambient Pressure Superconductor." This was research done by Q Center in South Korea, in Seoul. Seoul.
Yeah, Seoul.
It's in a place in Korea.
Yes.
And yeah, controversial all the time. So, well, I'm gonna be spoiler up front. So, context for this paper was submitted to the archive initially in July 23. At the time of recording, almost a year ago.
Mm-hmm.
And they then followed this up. Well, actually, I think it was on the same day. I think they popped 2 papers up to the archive on the same day, but there was a second paper, all in the show notes.
The second paper as well was had different or more authors. So maybe.
Oh, did it? I didn't know that.
So maybe they were rushing for credit.
Yeah. I think the whole nature of room temperature superconductors is all aboard the hype train.
I think people rush because I was watching some YouTube videos and one of the guys says like the person that actually makes one that's repeatable and valid is an instant Nobel Prize winner. You know,
it's kind of a big deal. So they followed it up. So had 2 papers, and then that second paper they refined a little bit, and by August or so, and then there were 3 other papers I noted submitted in August by other research groups that were challenging aspects of it. And like the TLDR, like if we were to just summarize the whole arc of events, was that they concluded that there was either an experimental error or there was some oddities in the synthesis of, or the manufacture of the material, and it's not a superconductor. But I felt like...
There you go. Thank you so much for listening to this episode of Osmosiscast. We'll see you next week.
But what we could do today is we could consider, what if this was the thing?
Yeah, so why is it such a... so before we get into the what if, do you want to talk about... Is there anything in the paper that you want to zoom in on? It feels kind of redundant given the preamble we've just done, but are there any of the figs that you want to point out?
I feel like an even preamble before we even get to the paper was just a bit of groundwork of what is a superconductor and why should people care. Not that this is a podcast about selling people on superconductors, but I don't know.
Hey, we sold people on Hyperion last week, so
yeah.
So go on then. So let me tell you what I think a superconductor is, and you can correct me or say well done. Sound good?
Say more. Yeah.
So my understanding of a superconductor is it is a material that provides 0 electrical resistance. So you would have waste-free power transfer, for want of a better... Is that accurate?
Yeah, I think so.
Cool.
That's how I understand it anyway.
Awesome. Thank you so much for listening to this episode of Osmosiscast. We'll see you later. We'll see you next week.
Yeah, that's it. That's like the high level awesomeness. What else can it do? It's got it's impervious to magnetic fields. So there's the Meissner effect, which describes the surface of the superconductor is impermeable to magnetic fields, which is, I guess, kind of a cool thing. I'm assuming that has applications.
Yeah, I was reading about how when something is a superconductor, so like the levitation effect that you can see.
Yeah.
So the science behind that is the magnetic field lines are effectively being expelled from the material in some weird sciencey way. I was thinking though, it's kind of like this is like real life magic. So people say there's like no magic.
It is.
People say there's no magic. Why do we live in a world without magic? We kind of do, don't we? It's just a very complicated magic system.
It's a complicated magic system that some people understand and most people don't. That makes it magic. That is, I feel like if you were to think about a magic trick, the definition of a magic trick is some people understand this, most people don't.
Yep.
It's magic.
Yeah, definitely magic. So go on. Tell me more about what a superconductor is and why we care about it.
So I did a little bit of reading, and this is straight from the literature. So superconductivity was first discovered in 1911. I'm not going to pronounce the name, but it was by some Dutch team of researchers. They had mercury. They made it really cold at minus 269 degrees Celsius, which is only 4 Kelvin above absolute zero for those who care. And they noticed that it was superconductive, or it was just resistance.
I'm laughing at 4. It's 4 Kelvin above absolute zero. Isn't that just 4 Kelvin?
Yes.
You could have said it's only 3 Kelvin above 1 Kelvin.
Yes, I could have said that.
That's just a weird way of phrasing it. I don't know. I wasn't anticipating it. I like it. I'm here for it, you know.
And yeah, so they discovered this, and if you make it hotter, it loses its superconductivity. If you throw it in a really strong magnetic field that like shatters the illusion, then it also loses its superconductive magic. So it's like a fragile state that things can achieve and attain at really cold or really extreme environments.
So what sort of things do we use superconductors for at the moment? My short list is like MRI machines, trains, and in some cases I was reading about a place in Korea that was using liquid nitrogen cooled cables to distribute power, because basically they didn't I should have written this down. It was basically they didn't have space to build bigger transformers for like to place more overhead cabling in, so they basically invested loads in like superconductivity. I might see if I can find it while you preamble a little bit more.
Yeah,
I mean, it's not really a preamble
much
anymore, is it? This is just the amble now, isn't it?
Oh, I think so. Yeah, I didn't have much on application. That's kind of what I had. So MRI imaging, I've never been in one, but big magnets. I'm assuming the important thing is that they're really strong magnets, and with superconductors you can make really strong magnets, which feels like a weird thing to say, but you can do really strong magnets, and it's not like it's magical energy coming from nowhere to like achieve this. Typically, you have to go down to liquid nitrogen, liquid helium temperatures, which is
cold.
Like, that is crazy to do. Like the infrastructure and services you need to do that. Like we had back in my masters, we had our lab in the basement, and you had like a joule of liquid helium in the corner, and to get that and then like maintain temperature stuff and get that to your like thing that needs to be really cold, it's really, really not trivial. It's not a back garden experiment.
No.
Yeah. Cold stuff. Difficult. The other thing I noted it was used for is in CERN, so for particle accelerators. Again, where they want really strong magnets to bend a particle around a tight corner, they can use superconductors. It's just really expensive in energy.
Very expensive. So let's talk about the fact that LK-99 was ambient pressure, room temperature. What are the implications of room temperature, ambient pressure superconductors then? Why was that such a big deal?
It's a big deal because if you can, like, the properties of a superconductor are, we've discussed, they are magic. If you can do magic somewhere where it's not an extreme environment, so where there's super cold temperatures. So there have been a lot of other superconductors that have been discovered and synthesized that can be high temperature. It's really funny. The classification for high temperature superconductor, if I recall correctly, is above 30 Kelvin. What's that? Minus 240 degrees Celsius. Come on. That's largely a historical artifact, but it's really cute. So a high temperature superconductor.
Isn't really that high temperature. In fact, it's interesting because I have this conversation with my year 11s and year 10s all the time. Like this concept of hot and cold. I feel like hot and cold is a really human construct. Like we think of cold as being 0, but that's not really that cold. Likewise, when we talk about freezing, and I would talk to them about metals. Well, a metal's still freezing at 1,000 degrees, which you would consider very hot. So this is certainly for people that are sort of starting out in science. The concept of hot and cold is a tricky concept to get your head around.
Even in the lab, I recall. So we had one of our labs was a high. We had two labs. One was a low to medium temperature radiation thermometry, one was high temperature radiation thermometry, and even lower down in the corridor where there's a high temperature and a low temperature like thermocouple, they mean completely different things. Like low temperature for us is like minus 40 to, I don't know, what on earth will it be? 500 or so? And then 1,000 is medium temperature, and then high is 3,000. But like to other people,
and you're talking in Celsius there because you said minus 50.
I am. Yes.
We should probably pick a temperature scale and stick to it, because it might get confusing.
I'm not gonna. We should always ascribe units.
Yeah, the teacher in me's coming out. Tell me your units. What are your units?
Really, that is the solution.
Yeah.
Well.
I don't remember. Are you okay? You have a bit of a cough today. Are you dying?
No, I should have brought my water.
Oh,
I forgot my drink.
I mean, go and get it. We can do a cut. Like, go and get your water. Don't sit here and die on my account.
I'll be all right. So high temperature stuff. If you can do a high temperature stuff, like you prefaced in the outset, the person who does this is going to be, I don't know, super famous. It's a really cool thing.
Quite rich.
Yeah, if the team that can achieve it will be onto something. That's why, this team was.
Why don't we do it?
Super hot on it. Let's do it. What do you know about phase transitions and shenanigans?
Little, but I think
I know water melts.
With your brains and my
ingenuity.
Yeah, let's go with that. We can achieve anything.
Let's do it.
Let's just get some cash.
Awesome.
Yeah, yes. Amazing.
So team was interested. So there have been in the meantime since 1911 there have been high temperature superconductors. There have been some superconductors. I think it was like 200 Kelvin or so. So that's like comparatively hot. But they require gigapascal pressures, which I don't even know what that translates to. Gigapascal.
A lot.
10 to the 9. I think it's only like 1,000 atmospheres.
Yeah, but that's still a lot, right? That's
that's quite a lot.
That's exponentially going to increase cost.
Yes.
Because and again, I'm gonna bring it back to the stuff we talk about in school when we talk about so we do a whole topic on rates of reaction and we look at like the Haber process. Where
I know this thing. I went through this recently.
Really?
Tell me more.
So in the Haber process is sort of the de facto reversible reaction we talk about at GCSE. We talk about the point of equilibrium being able to be altered with pressure or temperature, and we talk about the cost analysis effectively of, well, I could increase the pressure, but that's going to cost a lot of money. I could increase the temperature, that's going to cost a lot of money. So it's all about finding the happy sort of medium point, if that makes sense.
Yes.
So I imagine it's similar with superconductors in the sense that, sure, we could build this thing, but it needs this many atmospheres of pressure.
Yeah, exactly.
Is it going to be worth it economically?
Yeah, and I would say it applies to superconductors because I assume they're still well, they're not really. But room temperature, ambient condition superconductors are still just a research thing. But like the applications that they would derive sport.
Well, I mean, I think about MRI. So
They would into
I
this,
needed to
yeah.
get an MRI on my back, right? I have a slipped disc on my lower spine, and it's freaking
Ouch.
painful sometimes.
Awful.
And the NHS in the UK have put me on a wait list for an MRI. Do you want to know how much they said? How long I'll be waiting? They said about 3 years. I was like, all right, fingers crossed it doesn't break by then.
My God.
Yeah. But I have a
nuts.
friend who works in an MRI clinic, and I said, well, how much would it cost me, just out of interest, to get like a full back MRI, you know? And she was like, about £1,500 to £2,000, which is not that. It's not that expensive, right? But just
That's a lot of
imagine,
money.
just imagine what would happen if they could use an ambient temperature superconductor in an MRI machine. What would be the medical implications of that? Not just for, you know, NHS use, but across the whole world. You know, MRI is critically important in looking for, you know, scanning for cancers and other things in the body. It's critically important for so many medical processes. Imagine if they were a little bit cheaper, or
I hadn't even thought about that.
Cheaper.
But yes, it would make things like that so much more accessible.
Mm-hmm.
Yeah, it would be good. Holy Grail. So everyone wants it.
I have a question.
Should we hit the paper? Okay, go on then.
Let me do one more question. So I was going to ask about sort of the implication of what it would mean for like maglev trains, because I'm assuming they have to be like cooled, but I don't know. I was just wondering if you know.
Not really. My understanding is, yes, they would need to be cooled because they're probably using the same type of superconductor that an MRI is using, like that type of not ambient condition. Yeah, they would be using that sort of thing. So they might not have to go down to liquid helium temperature, which is 4 Kelvin. They might have to go to liquid nitrogen, which is comparatively toasty, which is, I guess, what, minus 180 or so.
I'm just skimming a little. I just did a Google. So it's a superfine niobium titanium alloy embedded in a copper bus. When the superconducting wire is immersed in liquid helium, so it is immersed in liquid helium at minus 269 Celsius, which is what? That's like 5 Kelvin, minus 269, 4 Kelvin, something like that. It's minus 273, isn't it?
That's crazy.
They're
using liquid helium on maglev
helium,
trains.
Yeah.
Unbelievable.
Produces a powerful magnetic field, blah, 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 blah. Yeah, so again, that's going to be expensive to keep it cooled.
That's really expensive. That is probably why they are so niche.
And they are, because
I feel like they're just there
in Japan?
as a showcase.
Are they only in Japan?
I noted a couple. There was, I think the first one was in Birmingham Airport.
No, it wasn't.
I think it was. You can fact check me on that one.
There
was one in Birmingham. There's China. There's Germany. Japan.
I just googled, is the maglev working at Birmingham Airport? It said the first hit from locomotive.fandom.com wiki says the Birmingham Airport maglev is a defunct maglev system.
Yes, it's no longer, but it was, and I think it was the first.
Yeah, so it looks here. I mean, just a quick Google: Japan, Korea, China. So it definitely feels like look what I can do, rather than this is efficient and can be moved around. But I was also considering, like, I was looking. So if we think about superconductors as being lossless energy transfer, right? Imagine a world where we have a global energy system, not just with countries, and across there is, these ambient temperature superconductors connecting solar panels in Africa during the day, and that power can be taken over to America during their day, and vice versa. Like, that is a pipe dream, because I think even if the technology existed and worked, our governments wouldn't stop arguing enough to get anything built. But just imagine. Just imagine.
That would be magic.
Yeah, that would be magic. Talk to me about the paper.
All right, what do we got? So, what I nailed down for this paper. So, scope of the paper was they synthesized this this material, and then the paper was there to validate it. I think the second paper was talking a bit more on that synthesis method. So that
they did include a very detailed synthesis method because they wanted other people to repeat it, right?
Yes. Yeah. And so what they did is they measured a couple of properties. So to validate a superconductor is superconductive, you can look at its critical temperature. So you can have a look at, is it superconductive? Warm it up a little bit. Is it still superconductive? And at the point when it turns off and it loses its superconductivity, is the temperature, it's called the critical temperature. And I guess stepping back to how superconductivity is understood to work, at least in by some mechanisms, it doesn't, not all, is that the electrons wobbling through a crystal lattice, they are in Cooper pairs, so they're, let's read this.
So
electron
it's
groups into pairs and they form Cooper pairs. It's a coupling between the electrons and the phonons of the lattice. That's it. So phonons are like thermal vibrations through a lattice.
Yes.
And so the electrons are coupled with the phonons, and then the electrons move through the crystal without friction.
So if you think about electrons in a lattice of I guess I mean ions, I guess. If electrons are free, they must be ions, right?
Yeah.
So when those electrons move through in like a copper conductor, for example, if the material is not at absolute zero, those ions are wiggling, so they will slow down.
Yes.
So even a conductor, something we would consider a good conductor like copper or gold, it still has some resistance. So the idea is if you can slow the vibration down to a point, then those electrons are free to move cleanly through the lattice, unimpeded by wiggling particles.
So it's kind of like you're just making the whole lattice just a real chill place, and then the electrons are just there like whooshing.
It's my sort of jam, you know?
It's so chill.
Love it. So chill.
So you've got the critical temperature. You've also got the critical magnetic field. So in the same vein of if you start warming everything up, it starts wiggling loads. Everything will freak out and stop conducting so well. If you apply a really strong magnetic field, eventually it's going to permeate that. Like we described the Meissner effect earlier on. So the surface is impermeable to a magnetic field, and eventually with a strong enough magnetic field, it will say, "Yeah, I'm in." And then if you have that in the material, it will start disrupting all the lattice, so then you impede the motion of electrons again.
On Cooper pairs, when I was doing my reading, I initially misread it as copper pairs, and I was like, what?
I think there are copper. I think there is copper, maybe in LK-49. No, maybe there's a lead apatite. I think there was copper or cupracer. Yeah.
I just thought it was funny.
Cooper.
I feel like I have I've created a trend of like slightly misreading things, you know, and I'm just gonna go with it.
So these copper pairs, it would not be confusing whatsoever, I'm sure. So you've got critical temperature, critical magnetic field. There's the Meissner effect. So if you can demonstrate that it's impermeable to a magnetic field, I think that's the floating thing, right?
Yes, I believe so, because that's the point. So if you imagine, you know, your magnetic field lines, normally they run through the material. They get pushed out of the material, which is why things float instead of sit, is my understanding. But that's like a very basic understanding. It is. It's levitation magic. Yeah.
And then there's zero resistivity. So where we're talking about like unimpeded flow of electrons, and like you can have the magic wire. If you have your like little strip of superconductor and you put it in a circuit with a little power source and you apply current, then in principle, if you measure the voltage across that conductor, the voltage should be zero and V equals IR.
So resistance is zero.
Is that the right equation?
V is equal to I. That's Ohm's law.
Yeah, I can't remember that, but yeah, V equals IR. So if your V is zero, then your R is zero because you're applying. Yeah. Anyway, and then so if you demonstrate those couple of properties, then that was their green light to say, we've made this, we think it is this, because they described what it is. They gave some like characterization of how they manufactured it. And then it demonstrates these properties. That's it. You made a thing.
But
it's a superconductor. Go figure.
The spoiler alert is it doesn't, right?
The spoiler alert is it doesn't, yes.
So my question, and I don't know if your research around the paper extended to this. Mine certainly didn't. Maybe yours did. What was it that was wrong with this paper? What was it that was wrong with the material?
So there are a couple of different takes that I noted. There was... So the Max Planck Institute, they followed the recipe basically and synthesized LK-99, and they said it did not observe superconductivity. So the material, the cake they baked by following the recipe, it didn't taste
as good
as it didn't taste as good.
So are we just to take that? So like, I guess my question is, are the authors of this paper, did they know that it wasn't a superconductor, and was this sort of almost a malicious attempt to get some sort of credit, or did they have was there an instrument error, or did they do something wrong, or was there like a bad egg in the team that was fabricating results? I'm just wondering, it's interesting.
Yeah, I'd like to give the benefit of the doubt and assume that it was definitely the latter.
Yeah, that's fair.
Yeah, there's no point publishing it if no one can replicate it, because then no one's going to buy it. Yes, so the measurements they're doing, they're not... Basically, they're hard to make. So it's not impossible for there to be some measurement error, some slight irregularities with their experimental setup. That just means...
I can imagine it's a very sensitive science. Yeah,
like you're applying a current to this superconductor and you're measuring zero resistance. Well, is it zero resistance, or is it not quite connected properly? Like, it could be just something trivial like that. So, there's some aspects of it could just be experimental error. Yeah. There was also I don't know if there was another paper that said it looked different when they.
I think there was
that. Yeah, there was one other paper that said we followed the recipe and it came out chocolate cake as opposed to a
vanilla sponge.
Victoria sponge. Yeah. So, there's, I think, just
more research needed.
Hey! Yeah, it's always more research needed. Yeah.
I love that we said that in tandem. We did not plan that.
There was Max Planck Institute, they discredited it. There was a Beijing National Lab, and they said there's some things that look superconducting, like the resistivity and the magnetic susceptibility, but they didn't see it actually demonstrate zero resistivity. And there was another team that I think they did some measurement, like of the crystallographic structure. But they also did a bunch of modelling and analysis of what this sort of thing should behave like, and they said it's probably just looking at the analysis and modelling, it looks like it will just be a magnet rather than a superconductor. So there was, but like despite this, and paper comes out, it's like woo, and everyone's excited, hey, and then people say no, it's wrong. Like, it was still a really good arc of events, and
and actually, I feel like. You're right. I feel like the guys, I imagine they're not even that mad, because
no, man.
It is what it is. It's just the nature of progress, I suppose. Is there going to be failures? That is it Thomas Edison is credited with trying and failing to make a light bulb 100+ times before he made one that worked. I think, and I actually, this is me getting philosophical. I think that the beauty of science is that scientists are the best people in the world at changing their mind. Like, you show me a bit of evidence for something, I will change my mind to fit the evidence. And I think lots of humans could learn a lot from that aspect of the scientific method, and that's why I think that, like, even though LK-99 is not a ambient pressure room temperature superconductor, the fact that it was in the news and it got people excited, that's a big deal. That's a big deal. It's a lot of buzz. It's a lot of people talking. It gets people interested, and maybe those kids that are aged 15 who read that last year are going to be the ones that make one in 10 years time, and that's just exciting.
That's so
isn't it?
cool.
That's exciting.
So cool.
Yeah, definitely.
I think the other cool observation from this is not enough publications are of the crap that goes wrong.
Yeah.
Like, everyone wants to write the paper about, oh, we did this cool thing and it worked.
Yeah.
But so much research is done, fails, and you don't chat about it. But like, this is an example of that. But it's really helpful for that field in saying, we tried this thing and it didn't work. And that just like gives all following researchers an idea of, well, don't do this.
Yep.
Which is really helpful.
Yep.
Or be mindful. Yeah.
Yep.
So.
And this was originally published on the archive as well. This was originally published there. It wasn't put through a journal or anything. It was just chucked straight onto the archive, which I think goes back to this thought process. What is it? What am I trying to say? The idea that like science is what word am I looking for?
I got no clue.
I'm looking for accessible. Science can be accessible for everyone.
Yes.
Right? There are no boundaries and barriers to this research. It's just there. It is what it is. Let's talk about it.
Which is awesome.
I agree. Let's talk about the paper. Do you want to? Are there any interesting figs to point out here? I would quite like to look because I know the graph.
Well, you tell me. Where are we going?
Well, I want to look at the graphs in Figure 1, like A, for example, because this is. Why can I not zoom? Hello, computer. I have to do it manually, I guess. So it's this applied current against measured volts. There's that bit where it drops down to 0. Can you talk to me about that and help me understand it a little bit? Because I've seen these graphs before in terms of like that's a very characteristic curve of a superconductor, and I don't really understand why that is the characteristic curve. I was wondering if you could shed some insight.
I can't shed too much insight, but I can certainly look at the plot and tell you what I see. So at least looking here, we can see current on the x-axis, voltage on the y-axis, and so what we're expecting here is as you apply a current to a superconductor, where we were discussing zero resistivity, then the voltage should stay 0. And so what we see here is, like, for example, for a bunch of the curves at like 100 milliamps of applied current, the voltage is 0, which says, hey, look, I've got 0 resistivity.
So
there's a bunch of different colors, and we can see it from about like room temperature, so about 20 degrees Celsius, up to about 400 Kelvin. What on earth is that? 150 degrees Celsius?
Something like that, yeah.
And so what they're saying is, we can, even at these high temperatures of 400 Kelvin, we can still demonstrate some some zero resistivity. So superconductive
I
behavior.
imagine when scientists looked at that graph, they were like, this is probably too good to be true.
It's got to be, yes.
Yeah. Okay.
Yeah. So that's a plot of them showing that the what is that? I see. Yeah. So that's showing they have a large current window and a bunch of temperatures where it's superconductive. And yeah, I guess you can see the whole thing, the same thing for the magnetic field strength in Figure C.
Can I just point you down? Can you go to Figure 3, Picture D? Right. Tell me when you're there.
3D. Yeah, I'm there.
What font?
Do you like that one?
What font is it?
Is it? I don't know. Is it Comic Sans?
It's Comic Sans. I like to imagine that's an in-joke. That's just an in-joke. Comic Sans. Yeah, I don't really understand these pictures, to be honest.
This is telling us about the crystallographic structure. I understand B. B is the brick.
B is a photo of grey stuff.
So what we can see here is just saying that it's like, you can't have a microscope that goes down and looks at what this structure looks like. So to understand what this has synthesized, you need to look at other methods. So like A is a model of like lead ions and other shenanigans. Figure C, so although it just looks like a couple of dots wiggling over the place, I understand it to be the electron density distribution.
Yes.
And this tells us about the crystallographic structure within the
which is
material.
way above my level of understanding and knowledge.
Yeah, it's pretty far for me too.
Yeah, we did.
It
I
tells you
remember
things.
at university. I did. I'm sure if not a module, definitely a few lectures on like electron crystallography. And yeah, I didn't really get it then. Didn't really get it then, to be honest. Very, very high level stuff.
I'm not super hot on this solid state stuff. Now, if we look at some like infrared spectrometer stuff, or just how any spectrometer stuff like that I get a bit more. But
yeah, I'm a bit more
this is crazy.
I'm a bit more comfortable with
be.
spectrometry and things. But yeah,
I get that. So figure 3 is just showing us a bunch about the structure, and I think there was another one. No, maybe not. But what I guess the thing to highlight here, so if we look at figure D, so if you're looking at the picture, you can see a couple of triangles, some red dots, and some blue dots, and some other blue dots, but there is a single of the dark blue dots, there is a single yellow dot, and that's their copper substitution. And so the mechanism by which they were describing in this paper of how it becomes superconductive is they take this lead apatite material, and then they dope it with copper. And by what I mean by that is they throw a bunch of copper in it, and that copper replaces some of the lead ions. So you're then imparting some stress, some like physical stress into the lattice structure. And it's that stress that then enables the flow of electrons, basically. So yeah,
just a very complicated magic system.
It's a magic system.
It's just a magic system. Okay. Anything else we want to talk about in this paper? I don't think so from me. As I say,
no, I think I'm pretty good. Oh, actually, well, let's give the final sentence a call out. It's epic.
Hang on, let me scroll.
The LK-99 has many possibilities for various applications, such as a magnet, motor, cable, levitation train, power cable, hoverboard, qubit for a quantum computer, terahertz, antennas, etc. So we believe that our new development will be a brand new historical event that opens a new era for mankind. Oh, yes!
Except, of course, thinking about what I said earlier on, none of the governments would agree to work together on it anyway.
Except for that.
Cynic. No, that's cool. I like that a lot.
Yeah, I thought that was.
It's a good sentence to point out. Definitely.
I don't know. I assume you haven't written any papers, Callum.
I wrote a dissertation. That doesn't count. That's it.
How did you tail off your dissertation? Like,
I don't even remember.
Because I for a bunch of my papers, that final sentence, I spent so long thinking about that final sentence. I'm just trying to find a quote from one of mine. But yeah, I spent far too long thinking about that final sentence, and like I want to leave the reader on a high.
Yep.
I want them to feel so good about I don't know, anything.
The prospect, you know.
Oh, that's a really.
But like the thing is, like arguably, if this room temperature ambient pressure superconductor had been repeatable and mass producible, it would have
been historical.
It would have been absolutely accurate to describe it as a new era for humankind.
Mm-hmm. Yes.
Mad to me.
Maybe my papers aren't that good. I feel like I did spend an inordinate amount of time.
I think your papers are great, Jamie. Don't put yourself down like that.
No. They've been all right.
Well, write a flipping good one then, mate. Come on.
I know. I just need to write a good sentence at the end. That's all I need.
The paper could suck, but if the sentence is good, then we're happy.
Yeah. No, I don't know. Anyway, that's superconductivity.
Yeah.
Which is
and we
cool.
mentioned hoverboards twice, so shout out to that.
Whoop, whoop.
I think we're done here. What do you think? You have any final thoughts? Anything you want to add before we close?
No, other than I think, like with all of the crap that we've been reading, this is again another really awesome field of science that I'm like, in another world, I would have liked to have spent some time in superconductivity. It's just a cool place of science. So anyone listening that is starting a career in science,
go research superconductivities, guys. It's pretty cool.
Yeah.
And you know, if you manage to make this, you will be one of the scientists that's taught in the classroom in 100 years. You will be. Like, that's just a fact.
You would.
Okay, awesome.
Make it happen.
I think we're done.
Nice. Thank you very much, Callum. This has been great.
Thank you very much, Jamie. It's been a lot of fun. Where are people able to find us if they want to?
I would point people to osmosiscast.com and go from there. There's a couple of little linky doos there. You can find us on Spotify, Apple, RSS, YouTube, places.
Perfect.
You can find us on places.
Well, thank you so much, audience, for listening. We will see you on the flip side. Thank you so much, Jamie, for your time. I appreciate it. And let's
take it easy, Callum.
Wrap it up there. Bye-bye.
Woo! Bye.